Transmitting event streams. In the batch processing world, the inputs and outputs of a job are files, perhaps on a distributed file system. What does the streaming equivalent look like? When the input is a file, a sequence of bytes, the first processing step is usually to parse it into a sequence of records. In a stream processing context, a record is more commonly known as an event, but it is essentially the same thing, a small, self-contained, immutable object containing the details of something that happened at some point in time. An event usually contains a timestamp indicating when it happened according to a time of day clock. See monotonic versus time of day clocks on page 288. For example, the thing that happened might be an action that a user took, such as viewing a page or making a purchase. It might also originate from a machine, such as a periodic measurement from a temperature sensor or a CPU utilization metric. In the example of batch processing with Unix tools on page 391, each line of the web server log is an event. An event may be encoded as a text string, or JSON, or perhaps in some binary form, as discussed in Chapter 4. This encoding allows you to store an event, for example by appending it to a file, inserting it into a relational table, or writing it to a document database. It also allows you to send the event over the network to another node in order to process it. In batch processing, a file is written once and then potentially read by multiple jobs. Analogously, in streaming terminology, an event is generated once by a producer, also known as a publisher or sender, and then potentially processed by multiple consumers, subscribers, or recipients. In a file system, a file name identifies a set of related records. In a streaming system, related events are usually grouped together into a topic or stream. In principle, a file or database is sufficient to connect producers and consumers. A producer writes every event that it generates to the data store, and each consumer periodically polls the data store to check for events that have appeared since it last ran. This is essentially what a batch process does when it processes a day's worth of data at the end of every day. However, when moving toward continual processing with low delays, polling becomes expensive if the data store is not designed for this kind of usage. The more often you poll, the lower the percentage of requests that return new events, and thus the higher the overheads become. Instead, it is better for consumers to be notified when new events appear. Databases have traditionally not supported this kind of notification mechanism very well. Relational databases commonly have triggers, which can react to a change, for example a row being inserted into a table, but they are very limited in what they can do and have been somewhat of an afterthought in database design. Instead, specialized tools have been developed for the purpose of delivering event notifications. Messaging systems. A common approach for notifying consumers about new events is to use a messaging system. A producer sends a message containing the event, which is then pushed to consumers. We touched on these systems previously in message passing data flow on page 136, but we will now go into more detail. A direct communication channel like a Unix pipe or TCP connection between producer and consumer would be a simple way of implementing a messaging system. However, most messaging systems expand on this basic model. In particular, Unix pipes and TCP connect exactly one sender with one recipient, whereas a messaging system allows multiple producer nodes to send messages to the same topic and allows multiple consumer nodes to receive messages in a topic. Within this publish/subscribe model, different systems take a wide range of approaches, and there is no one right answer for all purposes. To differentiate the systems, it is particularly helpful to ask the following two questions. What happens if the producers send messages faster than the consumers can process them? Broadly speaking, there are three options. The system can drop messages, buffer messages in a queue, or apply back pressure, also known as flow control, i.e. blocking the producer from sending more messages. For example, Unix pipes and TCP use back pressure. They have a small fixed size buffer, and if it fills up, the sender is blocked until the recipient takes data out of the buffer. See network congestion and queuing on page 282. If messages are buffered in a queue, it is important to understand what happens as that queue grows. Does the system crash if the queue no longer fits in memory, or does it write messages to disk? If so, how does the disk access affect the performance of a messaging system? What happens if nodes crash or temporarily go offline or any message is lost? As with databases, durability may require some combination of writing to disk and slash or replication. See the sidebar replication and durability on page 227, which has a cost. If you can afford to sometimes lose messages, you can probably get higher throughput and lower latency on the same hardware. Whether message loss is acceptable depends very much on the application. For example, with sensor readings and metrics that are transmitted periodically, an occasional missing data point is perhaps not important, since an updated value will be sent a short time later anyway. However, beware that if a large number of messages are dropped, it may not be immediately apparent that the metrics are incorrect. If you are counting events, it is more important that they are delivered reliably, since every lost message means incorrect counters. A nice property of the batch processing systems we explored in Chapter 10 is that they provide a strong reliability guarantee. Failed tasks are automatically retried, and partial output from failed tasks is automatically discarded. This means the output is the same as if no failures had occurred, which helps simplify the programming model. Later in this chapter we will examine how we can provide similar guarantees in a streaming context. Direct messaging from producers to consumers. A number of messaging systems use direct network communication between producers and consumers without going via intermediary nodes. UDP multicast is widely used in the financial industry for streams such as stock market feeds, where low latency is important. Although UDP itself is unreliable, application-level protocols can recover lost packets. The producer must remember packets it has sent so that it can retransmit them on demand. Brokerless messaging libraries such as ZeroMQ and Nanomsk take a similar approach, implementing publish/subscribe messaging over TCP or IP multicast. StatsD and Brubeck use unreliable UDP messaging for collecting metrics from all machines on the network and monitoring them. In the StatsD protocol, counter metrics are only correct if all messages are received. Using UDP makes the metrics at best approximate. See also TCP versus UDP on page 283. If the consumer exposes a service on the network, producers can make a direct HTTP or RPC request. See data flow through services, REST and RPC on page 131 to push messages to the consumer. This is the idea behind webhooks, a pattern in which a callback URL of one service is registered with another service, and it makes a request to that URL whenever an event occurs. Although these direct messaging systems work well in the situations for which they are designed, they generally require the application code to be aware of the possibility of message loss. The faults they can tolerate are quite limited. Even if the protocols detect and retransmit packets that are lost in the network, they generally assume that producers and consumers are constantly online. If a consumer is offline, it may miss messages that were sent while it is unreachable. Some protocols allow the producer to retry failed message deliveries, but this approach may break down if the producer crashes, losing the buffer of messages that it was supposed to retry. A widely used alternative is to send messages via a message broker, also known as a message queue, which is essentially a kind of database that is optimized for handling message streams. It runs as a server, with producers and consumers connecting to it as clients. Producers write messages to the broker, and consumers receive them by reading them from the broker. By centralizing the data in the broker, these systems can more easily tolerate clients that come and go, connect, disconnect, and crash, and the question of durability is moved to the broker instead. Some message brokers only keep messages in memory, while others, depending on configuration, write them to disk so that they are not lost in case of a broker crash. Faced with slow consumers, they generally allow unbounded queuing as opposed to dropping messages or backpressure, although this choice may also depend on the configuration. A consequence of queuing is also that consumers are generally asynchronous. When a producer sends a message, it normally only waits for the broker to confirm that it has buffered the message and does not wait for the message to be processed by consumers. The delivery to consumers will happen at some undetermined future point in time, often within a fraction of a second, but sometimes significantly later if there is a queue backlog. Some message brokers can even participate in two-phase commit protocols using XA or JTAC distributed transactions in practice on page 360. This feature makes them quite similar in nature to databases, although there are still important practical differences between message brokers and databases. Figure 11-1. A load balancing, sharing the work of consuming a topic among consumers. B. Fanout, delivering each message to multiple consumers. Figure 11-2. Consumer 2 crashes while processing M3, so it is redelivered to consumer 1 at a later time. Databases usually keep data until it is explicitly deleted, whereas most message brokers automatically delete a message when it has been successfully delivered to its consumers. Such message brokers are not suitable for long-term data storage, since they quickly delete messages. Most message brokers assume that their working set is fairly small, i.e. the queues are short. If the broker needs to buffer a lot of messages, because the consumers are slow, perhaps spilling messages to disk if they no longer fit in memory, each individual message takes longer to process, and the overall throughput may degrade. Databases often support secondary indexes and various ways of searching for data, while message brokers often support some way of subscribing to a subset of topics matching some pattern. The mechanisms are different, but both are essentially ways for a client to select the portion of the data that it wants to know about. When querying a database, the result is typically based on a point-in-time snapshot of the data. If another client subsequently writes something to the database that changes the query result, the first client does not find out that its prior result is now outdated unless it repeats the query or polls for changes. By contrast, message brokers do not support arbitrary queries, but they do notify clients when data changes, i.e. when new messages become available. This is the traditional view of message brokers, which is encapsulated in standards like JMS and AMP and implemented in software like RabbitMQ, ActiveMQ, HornetQ, Cupid, TIBCO Enterprise Message Service, IBM MQ, Azure Service Bus, and Google Cloud Pub/Sub. When multiple consumers read messages in the same topic, two main patterns of messaging are used, as illustrated in Figure 11-1. Load balancing: each message is delivered to one of the consumers, so the consumers can share the work of processing the messages in the topic. The broker may assign messages to consumers arbitrarily. This pattern is useful when the messages are expensive to process, and so you want to be able to add consumers to parallelize the processing. In AMP, you can implement load balancing by having multiple clients consuming from the same queue, and in JMS it is called a shared subscription. Fan-out: each message is delivered to all of the consumers. Fan-out allows several independent consumers to each tune into the same broadcast of messages, without affecting each other, the streaming equivalent of having several different batch jobs that read the same input file. This feature is provided by topic subscriptions in JMS and exchange bindings in AMP. The two patterns can be combined. For example, two separate groups of consumers may each subscribe to a topic, such that each group collectively receives all messages, but within each group, only one of the nodes receives each message. Consumers may crash at any time, so it could happen that a broker delivers a message to a consumer but the consumer never processes it, or only partially processes it before crashing. In order to ensure that the message is not lost, message brokers use acknowledgements. A client must explicitly tell the broker when it has finished processing a message so that the broker can remove it from the queue. If the connection to a client is closed or times out without the broker receiving an acknowledgement, it assumes that the message was not processed, and therefore it delivers the message again to another consumer. Note that it could happen that the message actually was fully processed, but the acknowledgement was lost in the network. Handling this case requires an atomic commit protocol, as discussed in Distributed Transactions in Practice on page 360. When combined with load balancing, this redelivery behavior has an interesting effect on the ordering of messages. In Figure 11-2, the consumers generally process messages in the order they were sent by producers. However, Consumer 2 crashes while processing message M3, at the same time as Consumer 1 is processing message M4. The unacknowledged message M3 is subsequently redelivered to Consumer 1, with the result that Consumer 1 processes messages in the order M4, M3, M5. Thus, M3 and M4 are not delivered in the same order as they were sent by producer 1. Even if the message broker otherwise tries to preserve the order of messages as required by both the JMS and AMP standards, the combination of load balancing with redelivery inevitably leads to messages being reordered. To avoid this issue, you can use a separate queue per consumer, i.e. not use the load balancing feature. Message reordering is not a problem if messages are completely independent of each other, but it can be important if there are causal dependencies between messages, as we shall see later in the chapter.